So here we go. This is now the big project. You are asked to work out the speed of density-driven flow. What's the speed of these flows? What does the speed depend on? What controls the speed of these flows? What to expect? Okay, this is a very important part of the scientific method, is to work out, to come up with conceptual ideas, to develop, to write up an hypothesis. Again, here we go. I produced a little sketch on the left side. Okay, let's see whether I can. Here, stars, this is my sketch. And I wrote down symbols for what we call scales. For example, the height scale is something that I call H, capital H. And if I write down an H, it actually means that I know the value of it. Okay, this is a parameter, so I can run an experiment where H is 20 centimeters. And that's the important bit. So this one is sort of a known parameter. What we also know is what are the densities, and the densities are called here rho 2 and rho 1. And we know what the density difference is, rho 2 minus rho 1. We already assume that the individual densities don't matter. The only thing that matters is actually the difference. If the density in the entire tank is rho 2, there will be no density-driven flows. It's only about the difference. And the height scale H. So now let's do some thought experiments. We look at different scenarios, and this is to simplify the problem. For example, scenario 1. Assume that you always use the same height H. What you do is you vary the density difference. There will be no flow or whatsoever if you have no density difference. If delta rho is 0, nothing will happen. But you get flow if you have a positive difference, if delta rho exceeds 0. So it's pretty straightforward to assume that the speed should increase with larger values of the density excess. Oh, that's already one hypothesis, and it's even more than an hypothesis, because this is a trivial. It's trivial that you get no flow at 0 and you get a flow if for larger value. Okay, so this is one scenario. All right, let's look at the second possibility. The second possibility is you always use the same density excess, the same density difference. Okay, the only thing you change is the height. You start with 0, you get no flow because you have no fluid. Whoa. You increase the height, you get flow. You get density-driven flows. And it's also reasonable to assume that if you have increased the H, if you increase the height, you get stronger flows. Because you know that with the knowledge that you actually increase the pressure gradient. So speed should increase with a larger value of H. There's a typo here. Okay, this has to be, I changed the state. However, now what you do now at the end is you combine both scenarios. It is reasonably to combine these two scenarios such that, well, you should get, it should be proportional, the speed should be proportional to the product of the density excess and the height. Okay, the product, which means that you could increase the density excess but decrease the height, and that leads to a compensating effect. Okay, so that's the hypothesis, but it's not necessarily a linear relationship. It might be some function. It could be a quadratic or a square root, something like that. Okay, this is why I write f. F means function. Okay, so this is something for you to really learn, to develop these conceptual models. What are the scales? What are the important parameters of your problem? And write them all down. And then do some thought experiments. What happens if only one parameter changes? What happens if the other parameter changes? And then try to work out what happens if more than one parameter change. Okay, so this is pretty cool stuff, and it's very important as part of the scientific method. So thank you very much. Thanks for watching this tutorial on density-driven flows. All right, cheers.